In this lesson, we're going to look at the idea of distance in R2 and R3. To get ourselves started, we'll think about R2 first. It's kind of the easiest way to visualize it. So the shortest distance between a point and a line always has to make a right angle. So if you think about this as a right angle, this would be my dot. This would be some sort of line in Cartesian form. I can figure out the distance between them if I use the idea of a scalar projection. That is, if I were to know some other point on the line, we'll call this point A, and this is the point we're trying to find, I can take the vector AP and project it onto my normal. And we know a projection works by dropping from the head at a right angle onto another vector. So if you think of this as our normal, and we think of this vector as AP here, if I were to do the scalar projection of AP onto N, I'd be left with a distance from here to here. In other words, the distance I want, the shortest distance between the point and the line. So a brief reminder about scalars, projections. If I take AP and I dot it with N and divide by the magnitude of N, I can figure out my distance. Now the only challenge is that the point A can move around. It could be anywhere you want on that line. So we actually have a formula that takes this idea of a dot product for any point A and our Cartesian equation, and we actually combine them together to create this equation. So here's our fancy equation for the distance between a point and a line in R2. Okay. A, B, and C are your Cartesian equation. So A, B, and C. Okay. The XO, YO is the point you want to figure out the distance to, and we're going to divide by the magnitude of the normal. Okay. One little thing I need to point out in this question, or sorry, this formula, is these signs here. Because we're producing a scalar value when we put numbers in, these actually represent absolute signs, as opposed to the idea of a magnitude sign. Yeah, so let's look at the first example, just get an idea of how this works. So my Cartesian normal values are A, B, and C. The point that I have, there's my X and my Y. So my distance is going to be the absolute of A, which is 5, times the X value, B, which is -3, times the Y value,
Mr. Churcher, please contact the office. Mr. Churcher, please contact the office.
and C, which is 15, all divided by the sum of the magnitude of the normal. So 5 squared plus -3 squared. So on top, we'll figure out all the parts inside the absolute signs, and whatever the sign comes out to, we make it positive. So we get 30 minus 12 plus 15, which gives us 33. On the bottom, we get the root of 34. You can leave it that form if you want to, which is exact. Or if you want to change into decimals, you can say 5.66 units. And you guys can try the second one. Same idea, just a point. So you want to go from a point.
Jalen Nathan, please come to the office. Jalen Nathan to the office.
There's your X and your Y. And unfortunately, they gave us a vector form for a line. We don't really want vector form, we want our Cartesian form. So for Cartesian form, AX plus BY plus C, we need to get our normal. The normal is the perpendicular to the direction. Here's my direction, so my normal, swap, change one sign. I now know 3x, 4y plus c is 0. To get c, I need a point. Here's our point. We can solve for c. Okay, if we add up all the things on the left side, we get -10 plus c. So c is 10. And now I got myself an equation. 3x plus 4y plus 10 equals 0. If I combine the point with the line, I can figure out the distance between them. So my distance will be the absolute of 3 times 15 plus 4 times -9 plus 10 over the magnitude of our normal, so 3 squared, 4 squared. which gives us on top 45 minus 36 plus 10, which is 19, and on the bottom root 25, or just 5, which gives us 3.8 units. Okay, and that's how R2 works. R2 is pretty basic to work with. If we move to R3, we can use some of the same ideas, but we're going to have a challenge here. Because in R3, we don't have Cartesian equations of lines. We have scalar, parametric, vector, but not Cartesian. So what we have to do instead is we have to use the idea of a cross product. Because that's going to produce a perpendicular line. So to do R3, there's two things we need to know. Number one, we need to know the direction our line is actually traveling in. So we need to know an M. Okay? And again, like the previous thing, you need to know a point on that line and use it and the point you want to figure out the distance to create a vector. We can then take our idea of a cross product, and that's the cross product of your direction here and your vector up here, we'll call this QP, okay, and produce a perpendicular vector. So a cross product does. Well, if we take that perpendicular vector and project it onto our normal, we'll end up with this formula right here. Okay, so formula for our distance here takes the direction of your line, the direction between a dot on your line and the dot you want to find, the distance between them, and you divide by the sum of your magnitude again. So the magnitude of your direction again. Okay, just to point out this time, these are magnitude signs. Because when you do a cross product, you produce a vector. And one of the sides of that vector. Okay, so we'll try one of the basic ones. Okay, the direction of my line obviously is 0, 1, 1. I want to figure out the distance from that line to this point. If I know a point on my line, call it Q, I can figure out a vector that joins these two things together. We'll call that PQ. You could also do QP, nothing wrong with that. Vector subtraction says I get 0, 1, negative 7. Okay, so the way my distance is going to work is I'm going to take the cross product of M and PQ, and the order you do this in does not make a difference because you're taking magnitude down the road anyways, over the magnitude of M. So let's give this a try. Let's do a cross product. Good practice here. So we'll do 1, 1, 0, 1, 1, negative 7, 0, 1. And our cross product produces a vector. So we'll get negative 7 minus 1. We'll get 0 minus 0. And we'll get 0 minus 0 over the magnitude of our direction, which was 0 squared, 1 squared, and 1 squared. And you make sure you're using M for that. That's the direction of our line. Okay, on top, we're taking the magnitude of that vector. So it's the square root of negative 8 squared plus 0 squared plus 0 squared. On the bottom, we end up with root 2. So up top, we get root 64, which is just 8 over root 2. And okay, if you leave it like that, totally fine. If we change it to a decimal, 5.66. Okay, so this is slightly different this time because we have to use the idea of a cross product because there is no Cartesians in R3. But we then go back to an idea where we can use magnitudes. Let's take a look at the next one. What happens if we have parallel lines? Okay, if we have parallel lines, just thinking about it for a second, we have a line here, and we have a parallel line here. Well, parallel lines made up of an infinite number of dots that are all the same distance from your first line. So really this is the idea of a dot and a line, or a dot and a line, or a dot and a line. It doesn't matter which dot you pick from one of the lines, they're all the same distance from the other line. So if we recognize we have two parallel lines, well, that gives us a direction. In R3, we need a direction and a vector joining two dots. Well, here's one dot, and here's the second dot. If we call this A and B, we can make a vector that goes from A to B. So we'll get negative 2, negative 1, and 3. If I want to do my distance between this dot and this line, or you could do the exact opposite, I need to take the cross product. So 1, 3, 1, 1, negative 1, 3, negative 2, negative 1. So we'll get 3 minus negative 3. We'll get negative 2 minus, oh sorry, not negative 2, negative 6. Minus 3. And we'll get negative 1 minus negative 2. All over the magnitude of our line, which is 1 squared, 1 squared, and 3 squared. So up top, the magnitude will be 6 squared plus negative 9 squared plus 1 squared. On the bottom, root 11. If we simplify that, up top we'll get a total of root 118 over root 11. I'm okay if you leave it that way, or if we change it to a decimal, we get 3.28 units. Okay, so parallel lines really aren't any different. Okay, so last situation, points and planes. The nice thing about points and planes is we can go back to the Cartesian equation idea again, because planes have Cartesian equations. The only extra part is we have a z direction and a d value. But otherwise, it's exactly the same idea. We have a plane, we have a dot. I'm going to project that dot onto it. I can do that if I know a point and use a scalar projection. Okay, so the formula should look basically the same, except for now we have this, sorry, not that part. We've got this part, right? It's the only difference. Everything else is exactly the same. You're projecting along the normal of the plane. So we need Cartesian form, we need a point. Here's a point, here's Cartesian form. So my distance will be the, back to absolutes because we're creating scalars, 8 times 1 minus 4 times 2 plus 8 times 4 plus 3 all over the magnitude of our normal. Okay, so exactly what you would have done with lines in R2, you do with planes in R3. So up top, we can get 35. On the bottom, we get root 144, which is like 35 over 12. And you can leave it exact. We can change it to a decimal, which is 2.92. And again, I don't care if you leave exact or decimals. Okay, so let's talk about the idea of parallel planes. Well, parallel planes is like parallel lines. When you have a plane, and you have another one's parallel to it, that plane is really made up of an infinite number of dots. Each of those dots has the exact same distance between them. Okay, so all you need really is if you have a plane that you know is parallel. So if we look at these two, they have the same normals. They have to be parallel, different Cartesians. All I need is a point from one of the planes to use in the other equation. The easiest way to find a point is to find one of the intercepts. And by that I mean make x and y be 0 and solve for z, or y and z be 0 and solve for x. Your choice. So for instance, if I make x 0 and y 0 here, I'm left with 2z equals negative 4, bring the 4 to the other side, and z will be negative 2. Well, this point is on this plane, for sure, for sure, for sure. If I use that with my other Cartesian equation, I can figure out the distance between a point and a plane. So our distance is the absolute of 2 times 0 minus 0 plus 2 times negative 2 plus 16, absolute, over the root of 2 squared plus negative 1 squared plus 2 squared. And it totally wouldn't have mattered which plane you use to find your points. Just use the other plane when you're using the equation for distance. Okay, so I use points from the first one, so I had to use the 16 in the second one. That's the only real issue there, right? Okay, up top, we're going to get, what's that, 12. Okay, on the bottom, we get square root of 9, which is really 12 over 3, which is 4 units. And that one came out to a whole number. Okay, so there's distance. 3 equations. Kind of know which one to use, when to use them. Okay, lines in R2, planes in R3, or lines in R3. And there's some questions you guys can try. That's distance.